All right, so today we'll talk about generative adversarial networks, which we call GANs. It's a very popular, very famous model, and it's been a while since it's been around. I think it was proposed in 2014, but still it's very relevant. I mean, if you want to generate like high quality, sharp images, you probably want to use GANs rather than VAEs for some particular reasons that you'll be seeing in this class. By the way, are there any questions related to practice session 5, which was rather short because we already covered a lot of stuff in the autoencoder, and VAE is actually just I mean, theoretically there's a lot of interesting stuff, but implementation wise, code wise, is just few lines of tweaking the autoencoder. You just add some stuff. You just add like the reparameterization tricks, and you just tweak the loss function a little bit, and then you have the VAE now. So it was a rather short tutorial. I mean, short practice video, but I hope that everybody is really clear on what they're doing. If there are any questions. If not, we can get started. All right. All right, so today, the contents are, okay, 질문 있습니다. 베리언스를 NN으로 만드는 것이 아니라 로그. 바를 NN으로 만든다는 것이 그 리파라메테이제이션 트릭 그때 그 베리언스 뽑을 때 그거 말씀하시는 건가 본데요. 인코더에서. 그 트릭이 왜 그랬어? 소정님 말씀하신 거가 맞나요? 로그를 씌워야 되는데 바가 음수가 나오면 안 되기 때문에. 그때 그 시기 뭐였는지 제가 잠시 까먹었는데. 네, 제가 DKL 시기 지금 잠깐 기억이 안 나는데, 어쨌든 그 말씀하시는 게 맞는 것 같아요. 두 분 다 그 유제부터 네네. 네, 어쨌든 그 시기 아마 방금 전에 그 소정님 써주신 것 같은데, 네. 어쨌든 그 DKL, 그러니까 KL 텀, 로스 텀에서 이제 그 리컨스트럭션 텀하고 로스 그 KL 텀이 있는데 KL 텀 쪽에 이제 로그 베리언스 들어가가지고 그렇다는 게 맞는 얘기 같네요. 저도 자세하게 여기까지 잘 기억이 안 나는데, 네. 어쨌든 그 성준님 말씀하신 대로 그 뽑을 때는 이제 뮤하고 이제 베리언스를 뽑게 되는데 베리언스는 음수가 될 수가 없으니까 이제 로그 베리언스를 뽑는 거가 네, 맞는 답이 될 것 같습니다. 네, 감사합니다. All right, so yep, all right, so we'll get started. I think this screen is being captured. All right, so today's topics, GANs, and then we're going to talk about the difference between VAEs, and there are another family of generative models. So like VAEs and GANs, they are both called generative models because they can generate new samples. typically images. They're used for generating images. These days you generate a lot of stuff, but typically back in the days it was usually images and sometimes maybe like sentences, which didn't work that well before with VAEs and GANs, but these days we use transformers to generate sentences, so it's a different story. Anyway, so there's VAE, and there's GAN, and then there's something called autoregressive models, which are, back in the days, it was the representative examples were pixel CNN or WaveNet or that kind of stuff, which we won't get into detail, but we'll just skim through it and then just see the difference between the three. Like all these three, the VAEs, autoregressives, GANs, they're all generative models, and we're gonna see what they are and like what's the difference and the pros and cons and stuff. And then we're gonna move on to how to evaluate the images generated from GAN, because it's rather not so straightforward compared to VAE, where we can use reconstruction loss to evaluate how well VAE is generating images, or the compression, how well the VAE is actually compressing and decompressing a given image. Compared to that, when you're using GANs, there's no straightforward way to evaluate how well it has learned to generate images. So we're going to talk about that a little bit. And finally, just a few modern applications of GAN recently, like something from 2016, 2017, 2019, like how GAN has evolved over time. All right, so starting from GAN. All right, the VAE recap. So I hope that everybody's already so fully crystal clear on what they did and how the VAE is, the working mechanism of VAEs. So objective is to compress X to Z, which follows a certain distribution, which follows a posterior distribution, such expressed as PZ given X, which is intractable. So, I mean, yeah, that's a true posterior, which is intractable, and then the next step is to decompress Z to reconstruct X, which is going to be our X prime. So here's an encoder, which as you can see is using the approximate posterior QZ given X, and then the decoder is the reconstruction step. And unlike the autoencoder, we want the latent representation, this one, the Z, we want this to follow a certain distribution. In our case, it was Gaussian distribution. So we use the KL term to regularize the latent representation. So typically this being the PZ being the Gaussian distribution, right? And what we did is to approximate, learn a approximate posterior QZ given X to mimic the true posterior PZ given X, which is intractable. So we use a QZ given X, and QZ given X, we typically use a parametrized model such as neural networks. So we use neural networks to learn a posterior that mimics the true posterior. And after we have successfully done that, after successfully learning or training the VAE system, we can sample from QZ, which can be converted to X. So I'm not sure if I've shown this picture from the last time, but for example, if you do right, so if you do a KL divergence, then if your true posterior it looks like this one here with the blue background, and you want to approximate it with Q, a approximate distribution, then it'll most likely try to cover a peak or a mode in your true distribution. So here, this is the largest amount or portion in the true distribution. So the Q will learn to cover that. So one mode, and this was like the characteristics of using the reverse KL. So after you've done that, then you can sample from your Q, and then the sample from your Q, and your X would most likely be it'll overlap with the sample from the actual distribution P here. So, but we will be missing a lot of stuff from here, but that's still that's kind of okay in the reverse scale. That's not the point in reverse scale. When you're using reverse scale or VAE, you want to sample from the most likely region. You want to, even if like at the sacrifice of kind of like ignoring some amount of distribution in your true distribution, you still want to sample like realistic examples. So you don't want to have something like this. You don't want your Q to look like this and then try to sample from here, right here, which in this case, the true distribution doesn't have a lot of doesn't have a lot of amount of probability or likelihood focused right here. So instead of doing like the forward scale with the reverse scale like this, and then try to sample like realistic samples. So this is what we did in VAE, and I hope everybody went through the practice, the code, so that they have a better understanding rather than just looking at the picture and then looking at the theories and the equations. You actually need to code it to really understand what's going on. I hope everybody did that. All right, so that's VAE Recap. And as I said, there's another family of generative models called autoregressive models. So this is like Pixel CNN. This is really kind of an old model that not a lot of people use these days. But back in the day, it was like one of the competitors in the generative models. So there was VAE, then there was GAN, then there was Pixel CNN. Pixel CNN was developed by researchers in DeepMind. So the essence or the core idea is to generate an entire image one pixel at a time. So here you can see an example here. So this, for example, let's say that your image is a 7x7 resolution. So there's 7 pixels here, there's 7 pixels here. And then what you do is given some initial pixels, like here, the blue ones are already given to you. So you're given all the blue ones already here. You want to predict what is the most likely pixel to come next right here. So it's the probability of pxi given xi minus 1, xi minus 2, all the way to x1. So that is your, and you do it, we call this autoregressive model because you do it autoregressively. So once you've predicted the xi, the ith pixel, you move on to try to predict the next one, xi plus 1 here. So that's, once you've done this, then you go over one more step and the I plus 1. You want to predict this one given xi minus 1, all the way to x1. And then again and again until you go to the very last one here. So it's an iterative process. It's autoregressive process. So it's a rather straightforward idea, like trying to guess one pixel at a time, but it works pretty well. And you can apply the principle to a lot of other domain, like audios or text. So for example, WaveNet came after Pixel CNN. I think this came in like maybe 2016 or something. And this here is also from DeepMind, researchers at DeepMind. So this time they generate audio 1 frame at a time. So when you listen to like MP3s, there's like sampling rate, right? So in a single second, there's like certain number of frames that is packed into a single second. So there's like a lot of wave pitches, and in the WaveNet, it's the same principle. They use CNN. They call something use a dilated convolutional neural network. So they use CNN and they generate 1 audio frame at a time. So you can imagine it's going to take quite some time to generate like few seconds of audio. And most recently, it's you can generate. I mean, GPT-3 was like, it took the world by storm. So, and they showed the state-of-the-art performance in generating sentences or even documents, like short documents or short articles. And the way they do it is they generate 1 word at a time. So you can see that there's like a common principle in all these models. They either generate 1 pixel at a time or 1 frame at a time or 1 word at a time. So they do it autoregressively. You do 1 pixel, then you move on to the next pixel, then you move on to the next pixel. Same principle in GPT. You generate one word, then move on to another word, then move to the next word, and then move to the next word iteratively. So these are all autoregressive models. Yep. So here, yep. So the principle is all here. So you have a likelihood or probability of your sample X. So, and you can break that down into, or you can factorize it into this kind of form. And your function p theta is usually a neural network. Like it could be in Pixel CNN or WaveNet, it was convolutional neural networks. In GPT-3, your p theta, your function was transformers. And it works for, as written here, it works very well, but it has a rather slow inference because you sample one pixel at a time, or you sample one audio frame at a time. So for example, if you're generating MNIST images, then you need to sample pixels 784 times. So it's like a for loop that goes on for 784 times, and that you can, if you imagine going a bit higher resolution rather than, because your MNIST is 24 by 24, but if you want to generate like MNIST images like 128 by 128 or 256 by 256, then you need a way longer for loop, and that's just gonna take quite some time. So that was kind of like one of the cons of like these autoregressive models. Yeah, same problem occurred in WaveNet. So just to generate like few seconds of audio, they needed to sample like several minutes to like maybe even like 1 or 2 hours. So it's sometimes it's impractically slow. Like the output quality is really like very good, but it's just that the sampling process takes too much time. And I guess the same problem could occur in GPT-3. Like it's not, I mean, sentences are not that long. I think, if I remember correctly, GPT-3, their upper bound for the length of the sentences, length of the document that GPT-3 can generate was 512 tokens, 512, not words, but like 512 word pieces. So the for loop, the upper bound of the for loop was 512. So it's rather bearable compared to like generating, I don't know, 128 by 128 image, which is like 16,000 like for loops or something. Compared to that, 512 for loop is much better. But yeah, so yeah, these are like the autoregressive family. And yet another generative model family. So VAE is an autoregressive, and then there's the third one, which will be the main character, the main topic of today, the GAN. So the question is, or the motivation is, what if we don't care about the data distribution? So in VAE, we approximated the data distribution. Well, we didn't approximate the data distribution. We approximated latent distribution, the QZ given X. I mean, the PZ given X. We didn't directly approximate PX. What we did is we approximated PZ given X, and then this was approximated by QZ given X, and then we could sample from like the approximate distribution rather than sampling from PX directly. So that was VAE. In autoregressive model, we explicitly modeled the data distribution PX by factorizing it into autoregressive form. So in this case, we could directly generate samples from the samples by using the autoregressive models, and that was directly modeling the data distribution. But what if we don't care about those at all? Like we don't care about the latent distribution, we don't care about the posterior, we don't care about the PX, we don't care about all of that. We just want to generate good synthetic samples. That's the only thing that we care about. And that's where GAN comes in. So obviously, we already talked about pros and cons a little. So in GANs, we don't care about the data distribution. So that means it's difficult to evaluate how well the model is doing, because everything is like, the data distribution, the latent space and all that, it's all ignored. So, but the image quality is good. So there's like very clear pros and cons, the good and the bad. Yeah, so the very simple architecture is drawn here. So you sample some random noise from the latent space. And it's just random noise. There's no structure there. You could either use uniform distribution, you could use Gaussian distribution. I think people use both. Yeah, you can use both. Doesn't really matter. I think people use uniform distribution a bit more often, but it's really up to you. So you just sample some random noise from maybe uniform distribution between -1 and 1. And then you put so that maybe you sample like maybe 10 dimensional vector from here. So your Z is like 10-dimensional vector, and it'll have some random meaningless values. So this is your Z. And then you put that through your generator network, which can hopefully massage or convert that Z into a proper looking image like this. So it'll like, expand the dimension, because this is only 10 dimension. This is only 10D, but you want maybe like 32 by 32 image that looks like a real photo. So you need a 10-dimensional image blown up into 32 by 32. So that will be taken care of by the generator network. So that's it. That's all there is to it, to the generator side of the GAN architecture. It's pretty simple, and it's all totally up to you how you want to compose your generator network. You could use NLP for it. You could use convolutional neural networks. You can use whatever, like some combination of all the fancy stuff. Doesn't really matter, but as long as it works, it's all good. Right. So moving on. So generator network, adversarial network is basically, it's a two-person game. So it's a game between generator, which converts the random noise into a proper looking sample, typically images. And there's that generator, and then there's the discriminator. And you can think of this in like a game theory type of thing, like where it's typically like there's something called prisoner's dilemma. Like there's two prisoners, and then they need to make a choice to maximize their gain, and something like, you can think of this like, you can think of the GAN in that context. There's like one person called generator, another person called discriminator, and they're playing a game to maximize their own benefit. And the game is for the generator, it tries to fool the discriminator by generating realistic fake samples, which I'll call X prime. So that's the goal of generator. And the objective of discriminator is to correctly distinguish between real samples, which I'm going to call X, and fake samples, the X prime. So the real samples are going to be given to discriminator from actual data, like real images, and the fake samples are of course generated by the generator G. So the goal of the discriminator D is to correctly distinguish like which is the real one, which is the fake one. So it's an adversarial game, because the generator tries to fool discriminator, and the discriminator tries to distinguish or put down the generator. So you can see it's a quite interesting concept. Right. So again, the architecture is very, very simple. So that we already talked about the generator side, the G side here. And all you need to add to that is the discriminator network right here. So D. So this is the G, this is the D. And of course, the G generates fake samples, the X primes here. And the real images X are coming from another channel. So discriminator, given X prime and X, tries to distinguish which one's real and which one's fake. So it's a real or fake, 1 or 0, right? So that means it's a binary classification. It's a binary classification for the D network, discriminator network. And very similar to the previous slide, you can compose discriminator network as you see fit. You can use NLP, you can use convolutional neural network, whatever. You can use whatever, as long as it has enough power to discriminate fake samples from real samples, it's okay. Right. So as I said, it's a binary classification. So it's just that there are two different sub-goals. So for G, the goal of the G is to fool the discriminator, which means it wants the binary classification. So the binary classification being classify real and fake. Successfully, I mean, successfully, hopefully. So that's the binary classification. And for G, if you fail the classification, that's good. That's the goal that's the objective that G wants to achieve. Because, the better the quality of the fake samples, then the worse the classification performance will be, right? So it wants to fail the binary classification, and for D, it wants to succeed the binary classification. So there comes the adversarial part. There comes the zero-sum game element here. Because for, it's a zero-sum game, because for G to win, the D must fail. And in order for D to win, the G must fail. So it's a zero-sum game. And if you are familiar with the zero-sum game and the game theory and all that, then you've probably heard about the Nash equilibrium, like John Nash from the movie Beautiful Mind, if you remember that. Like, he comes up with this thing called Nash equilibrium, where when there's like a zero-sum game and there are like multiple participants or multiple gamers playing the zero-sum game, then the optimal solution for the minimax game is like the same as the Nash equilibrium and all that kind of like the game theory type of thing. If you remember that, or if you ever learned that stuff in the undergrad or in your like economy classes, then you can probably like see the analogy between that and the GAN game here. So, like, theoretically in GAN, there's also this whole thing called like Nash equilibrium and all that, which in theory it looks all cool and it's pretty appealing, but in reality, in practice, we don't care that much about the Nash equilibrium and all that, because when you implement GAN, you already kind of deviate from the true minimax game. But you'll see what I mean. Yeah. Right. So since this is a binary classification, so we'll forget about all the minimax game and all that. We'll derive the objective of GAN one by one, like one equation at a time. So we'll start with the cross entropy, because we're playing a binary classification game. So of course, when we think about binary classification, we need to immediately connect that to cross entropy here. So hopefully this is very, very, very familiar now to everyone. So binary cross entropy. So, I mean, it's a negative cross entropy because there's a minus sign here. But if you just remove the minus sign, then this is your cross entropy. Right. And if you remember, there's the positive term and then the negative term. So if the sample is a positive sample, then you want to use this term to maximize your classification performance. If it's a negative sample, then you want to use this term. So if it's a positive sample, then your yn, your label would be 1. So this term would survive. If your sample is a negative sample, then your yn would be 0. So this term would survive, right? So it's a two case scenario. It's either positive or it's negative. And because of that, we can actually break that down, break this cross entropy down into two separate terms like this. So this is the positive sample term. This is the negative sample term. So we've already kind of like distinguished the two cases. So we don't need these. We don't need this and this anymore. So we're only left with the log terms here. So separating positive samples and negative sample. So this is, yeah. I've used M and I've used N here to represent the number of positive cases and number of negative cases. But hopefully, I mean, usually they should be the same. I just wanted to make it clear that they're different terms. But usually it's ideal if you have the same number of positive and negative samples, like 50-50, right? But this, like using M and N here, is just for like for the sake of argument. Yeah. Hopefully I just explained why I used M and N. 네, 그러니까 성주님 지금 제가 방금 말씀드린 게 뭐냐면 여기가 M이고 여기 N인데 사실 둘은 똑같이 그러니까 여기가 N인 거는 여기 N이랑 여기 N이랑 상관이 없어요. 사실 이걸 이제 뭐 M이랑 뭐 사실 뭐 이거를 뭐 J랑 K로 썼어야 되는데 뭐 굳이 이제 제대로 하려면은 아니면 뭐 2분의 0.5N이랑 0.5N 뭐 이렇게 써든가 뭐 이렇게 써야 되는데 그냥 이제 그냥 전개 과정에서 이제 뭐 n이랑 뭐 이런 건 신경 안 쓰고 단지 이제 여기에 이제 m 개의 포지티브 케이스가 있고 여기에 m 개의 네거티브 케이스가 있다. 그냥 이제 서로 다른 개수의 m 개랑 n 개의 서로 다른 개수의 포지티브 네거티브 케이스가 있을 수도 있다라는 걸 명시하기 위해서 굳이 그렇게 쓴 거예요. 사실은 뭐 정말 정확하게 하려면은 이제 뭐 포지티브 케이스 여기에 총 n개 샘플이 있었고 그 중에 반이 포지티브 그 중에 반이 네거티브였다. 그럼 이제 여기에 0.5n 0.5n 뭐 이런 식으로 갔었어야 되는데 뭐 그냥 그렇게 안 쓴 겁니다. 네. 괜찮으실까요?
근데 그런 경우에도 그 이퀄은 성립하지 않는 거 아닌가요?
어디에다 말씀하시는 건가요?
첫 번째 줄에
네.
n이 그중에
네.
그중에 뭐 0.7n이 포지티브고 0.3n이 네거티브였다 하더라도 그걸
네.
우리가 알고 있어서 둘째 줄 수식에 반영하려고 하더라도 그
네.
n분의 1은 전체 서멘션 전체에 대해서 첫째 줄에서 걸려 있던 거니까
네.
그 서멘션을 두 항으로 나눈다 하더라도 그 1 오브 n이라는 거는 그러니까 그 변할 수 없는 거 아닌가 싶어서요. 이퀄이 성립하려면 둘째 줄로 갈 때.
요 원오브N 요거 말씀하시는 거예요?
그러니까 첫째 줄에 있는 1 오브 n이 거기 두 번째 서멘션 앞에도 있어야 하고 첫 번째 서멘션 앞에도 1 오브 n이 돼야 되는 것 아닌가.
요거
그러니까
말씀하시는 거예요, 여기?
네. 그거는 그 전체 샘플 n개 중에 몇 개가 포지티브 샘플이었는지랑 무관하게 첫째 줄에서 n분의 1로 전체에 걸려 있었으니까
네.
그거를 분리할 수는 없는 거 아니냐는 질문. 그러니까 포지티브 샘플, 네거티브 샘플이 서멘션 항 안에서는 우리가 분리할 수 있지만 n분의
네네.
1은 그거 전체에 걸려 있으니까 그 걔네들의 구성 비율이 어떻게 되던 간에 n분의 1을 우리가 그 서멘션 앞에 있는 것들을 건드릴 수는 없는 것 아닌가 하는 의문이 들어서요.
그런가요? 네. 이거 쓸 때 뭐 그렇게 막 깊게 생각하지 않고 썼기 때문에 뭐 그러실 수도 있을 것 같은데. 어, 그러니까 지금 말씀하시는 게 굳이 이걸 분리를 한다 그러면은 여기 n분의 1은 살아남고 그다음 여기 또 n개가 있고 그다음 그 안에서 다시 또 나눠야 된다는.
그러니까 둘째 줄에서 그 n분의 1을 쓴 다음에 가로를 열고 두 개의 서멘션 항을 넣고 이제 그 다음에는 이 스몰 m 그러니까 두 번째 줄에서 두 개의 서멘션 항을 가로로 묶은 다음에 그 전체에 대해서 1 오브 n을 곱해주는 게 맞고 그 가로 안에 있는 서멘션의 개수는 말씀하신 것처럼 포지티브 샘플의 개수, 네거티브 샘플 개수로 이렇게 하는 게 이퀄이 성립하려면 그렇게 돼야 되는 거 아니냐 질문입니다.
네네. 그러니까 이제 n 소정님이 말씀해 주신 거랑 같은 얘기라는 거죠, 지금. n 썸의 개수는 jk가 맞네.
네.
서메이션 보세요. 분의 1 k의 퍼센트. 그런가요? 음, 음, 아, 이걸 제가 막 여기서 하기에는 조금 시간이 모자른데, 예를 들어서 뭐 100개가 있다 그러면 이제 여기서 뭐 얘가 뭐 50개 있었다. 그러면 이제 여전히 어쨌든 간에 끝에 여기서는 이제 100분의 1이었던 게 여기서도 100분의 1이 붙고 그다음 그 안에서 이제 다시 50개에 대한 텀이 이렇게 50개 텀 있고 50개 텀 있고 그렇게 된다는 말씀이신 거죠? 네네네. 근데 비율과 상관없이 30. 그렇네요. 네, 제가 착각했네요. 이 비율이 달라지면 더 큰 문제가 있구나. 네, 그렇네요. Okay, yeah. Okay, so I'm sorry about the mistake. So there should be I guess I didn't quite think it through when I was writing this equation last night. So Yep. So there should be n 1 over n still. So instead of yeah, yeah, let me just erase that. 1 over n, it should be sum over so let's say there's p positive cases and log y hat I plus sum over n negative cases. I'm going to use maybe I can use the same index here, log 1 over y I hat here, like this. So yeah, this should be the correct form here. In that case, I kind of lost the connection between the second line and the third line is quite quite illogical, I guess. Let's see if we can make that connection. 1 over n, so it becomes 1 over n, then yeah, so if they're the same number, I guess you need a little manipulation to go from 2 to 3, I guess. So you need to maybe do a bit multiply or divide the whole thing by some constant to make it to jump from 2 to 3, I guess. Right. So after the class, I'll try to correct this mistake and then upload a better version of the slide. But so the core message here is that you can start from the cross entropy and then try to arrive here by doing some manipulation. So you want to have the term for the positive cases and the term for the negative cases, and you can convert that into a expectation, because since what we're doing is actually doing expectation. When we're doing mini batch gradient descent, what we're doing with the mini batch is we want to, well, not even mini batch. If you do a full batch gradient descent, still like we have a fixed number of training samples in your training set, and that doesn't represent the entire, like all the possible data set you can get from the world. Like there's like there's like the population, and then there's the sample. You'll never have the entire population in your data set. You always have a sample of a population. So even if you do full batch gradient descent, imagine there's like imaginary, like entire, all infinite number of samples in the world, and that is your population. And then you take some, and that becomes you take some sample, and that becomes your training data. So this is your training data. And then you take like an average value, average gradient, or average like something from your sample, and that essentially is you're estimating the true characteristic of your population by looking at the sample. So that is why that's the analogy between starting from here and arriving at here. So taking a mean of something is actually just you're approximating the expected value. All right, so sorry for the confusion. So just remember that what we want is actually this term and this term to be separated. And what we're essentially doing is we're just sampling from some pot. So you can think of the first term as you have the x from some positive distribution. So there's like a distribution of positive samples, and then there's a distribution of negative samples. So there's like two different samples. Instead of having a single data distribution, you have two separate data distribution, which is like the positive side and the negative side. And then you sample from the positive side to get, and then you can estimate this value. You sample from the negative side and you estimate this value, right? Question from Rushta: why are the yn 1 minus yn not multiplied with the log terms for a separate VE and minus VE? Okay, so VE plus VE and minus VE. I'm not sure what you mean by V, Rushta, but I guess. Right, so I'm not sure what you mean by VE and minus VE, but it just I'm guessing that you're asking why we lost this term and this term here. So there's no more like term here. It's because we've explicitly separated the case. So we already know that the yn here would be 1 and 1 minus yn here would be 1, because yn is 1 in this case, in the positive case, and yn is 0 in the negative case, and 1 minus yn would be 1, right? So we no longer need these terms here. We already know that like the first term is all about positive cases and the second term is all about the negative cases. Yeah, okay. Cool. So moving on. So we have the expectation for log expectation value for the positive cases and log expectation value for the negative cases. And because we're dealing with real and fake instead of positive and negative, so it's still a binary classification. It's just that we care about the real samples and the fake samples in the GAN context, right? So we change the term here, positive to real, negative to fake. So there's now a real like distribution of real images, but not necessarily images, but real samples. But in GAN, is usually they're used for generating images. So I'm gonna use that like interchangeably. So there's distribution of real images, there's distribution of fake images. So we change the words from positive to negative, and then after that, if you remember that the way we generate fake images, the fake samples X prime is to sample from a noise, random noise, which could be uniform or Gaussian. We sample from random noise and then put that through a generator, and then the generator converts that Z into X prime, right? So instead of using P fake, we use PZ, which is random noise. So we sample from Z, we sample Z from PZ, like uniform or Gaussian, put that through the generator, and so GZ would be actually, this is X prime. So we simply replace X prime with GZ, the generator taking the Z and converting that to a fake sample. So that's how we make the jump from here to here. And then finally, because we want to learn such D and G in GAN context, so D and G must be some parametrized model that can be trained. So we put the thetas here, the parameters of the discriminator and the parameters of the generator. So theta D and theta G will be respectively, they'll be the parameters for the two neural networks. All right, so this is how we arrive at the GAN objective. So this is actually the GAN objective that you see in the paper. So this basically it's a cross entropy term. It's just that you did some manipulation to, change the positive to real, negative to fake, and then instead of the fake samples, we sample from the noise distribution, some random noise, and then so that's why we have the Z here. So it's a simple manipulation. I hope this is very clear to everybody. Just remember that this is just the motivation is just simple cross entropy, and then you just do some manipulation. All right, so for D, you want to succeed the binary classification. So for D, that means that you want to learn the parameter, you want to train the parameters of the D such that you want to maximize this term. You want to maximize or succeed the binary classification. So you want to maximize the cross entropy. Remember that when you are using cross entropy as a loss, you use the negative cross entropy, so that minimizing the negative cross entropy was maximizing the cross entropy. So that's what's happening here. You're maximizing the cross entropy. And for G, you want to fail. You want the binary classification to fail, so you do min. So you want to minimize this whole term. And so you want to train, or you want to learn the theta G value such that it'll minimize the entire binary classification term. And remember, and note that there are two terms here, and only the second term is concerned with the theta G here. So in the first term, there is no theta G. So you can just completely forget about the first term, and you're only left with the second term here. So you're only left with the term that has any concern, that is any relevant to the theta G here. So two terms, term for the D, term for the G, and then you have the two objective functions that you want to train. So all in all, it's a two-person minimax game between D and G. So for D, for the discriminator, you want to maximize it. You want to maximize this term. For the generator, you want to minimize this term. So it's a minimax game. So it's a zero-sum game between the two player D and G. So yeah, so the discriminator wants to maximize the objective such that dx is close to 1 for real and dgz is close to 0 for fake. And conversely, generator wants to minimize objective. It's the same thing as all over again. Right. So yeah, this is the final, like the one expression, the one equation that contains the essence of GAN. It's a minimax game between the two. Right. So theoretically, so I briefly talked about Nash equilibrium and all that. So it's a two-person game. It's a zero-sum game. So the solution to this minimax game is the same as the Nash equilibrium, and that means so when D and G reaches Nash equilibrium, I mean, theoretically they will reach Nash equilibrium. Like if you truly solve this problem, then it'll reach a Nash equilibrium. But in reality, you actually can't, because it's a neural network and you need to train that. So like you train D one time, and then you train G one time, and then you train D one time, you train G one time. So you alternatingly train D and G, and then so the fate is that they're destined to oscillate. Like you train one thing and then you train another thing, so they're oscillating. So you can actually not reach Nash equilibrium. But theoretically, if you think about like ideal situation where you can train like D and G at the same time, like they learn exactly at the same time, which is kind of which is not what we do in reality. But if you in theory, if you can do that, then you can reach Nash equilibrium, and that means when you reach Nash equilibrium, the D's accuracy is 50%. So that means that your discriminator is as good as randomly guessing if it's seeing fake or real. So it's complete confusion. So if D's accuracy is like 75%, then it is like 75% of the time it can distinguish the real and fake correctly. But if it's 50%, then it's as good as random guessing. So that means GZ's distribution, the generator has learned the distribution that is the same as the data distribution. So that's when Nash equilibrium is achieved. So the generator has learned the true distribution PX, and that means the D cannot do better than guessing randomly when given fake and real. So there's a bit of a iteration of how D and G learns. So this is your random noise Z, and then your G will learn to map. So this is your G. Your G will learn to map your random noise into some part of your true data distribution. So this is your GZ. And for example, let's assume that your true data distribution is like this. Like this. This is your true data distribution, PX. And initially, your generator is not doing a very good job. So its approximation is this. So this is your GZ, and this is your this little fluctuation here. This fluctuation here is the decision boundary for your or the confidence of your discriminator, because it's a binary classification. So once you've learned the G, once you've trained it, once you fix the G such that it maps your Z to this region, then you can train your D discriminator. You can update your discriminator so that it can correctly discriminate between samples from here and samples from here. So samples from here will be X prime, the fake. Samples from here will be the real. And then your discriminator can have a correct decision boundary or correct decision confidence between the two. So anything from here, anything from here, it should be 0. the dx prime from this region should be 0. So you can see a very low value here. And anything from here, like anything from here, here, it should all be 1. The discriminator output of this region should be 1 because they're real samples. So it has a high confidence. So now that you've learned the D, so now you've updated the confidence of D, now then it's time to update your G now, because it's an alternating process. So once so this is from here to here, you update G, you update your D. Now here, when you come from here to here, you update G. Update G. So once you updated G, you can, how you update G is you want to fool the D, you want to fool the discriminator. So in order to do that, in order to fool the discriminator, you need to move your discriminator distribution a bit left here, a bit leftward to the left. So that is why your new GZ has moved a little to the left in order to fool the discriminator, right? So, and eventually, if you do this process, if you keep doing this process like updating D, updating G, then again updating D, updating G, then sooner or later, like if you do it like a lot of times or maybe infinite number of times, then your G will be the same as your data distribution PX, exactly like this. And then in that case, your discriminator has no chance of actually, no chance of correctly distinguishing between the real ones and the fake ones. So its confidence is always like flat. It's 50-50. All right, so the question is, how can you adjust early stopping point using both generator and discriminator loss? And can it be different depending on the problem? How can you adjust early stopping point using both generator? So I guess the question is, when you look at the loss, so there were two, so I hope this part is clear to everybody. So this is like the kind of like graphical explanation of how they're tuned over time. And I guess what Sungjin is asking is, so there were two terms, two losses. So this is the generator loss, and this is, I guess this is actually, so this is your discriminator loss, and this is your generator loss. And I guess the question is, if you look at the two losses, like when you train the GAN networks, the discriminator generator, or alternatingly, and you look at the values for this, and you look at the values for this, can you determine when to stop the training? It's a very good question, because nobody really knows. Like I don't think until today, until these days, there's no like golden rule to know when to stop the GAN training. Because you don't really know, like, for example, as I said, just because, for example, at some point, your discriminator loss could be 0.5. Like the accuracy, I mean, your loss wouldn't be 0.5 because this is binary cross entropy loss. So you need to like calculate the accuracy of your discriminator from time to time. And let's say, assume that at some point your discriminator accuracy was 0.5, like 50%. Then can you really say that you've reached Nash equilibrium just because your D's accuracy is 50%? That's actually a no, because just because your accuracy of discriminator is 50% doesn't mean that your G has truly, learned the data distribution yet. So there's no guarantee that you've reached the Nash equilibrium just by looking at the accuracy of D. And conversely, just by looking at the distribution, just by looking at the loss term of G, just because like this term is like really low, doesn't mean that it has learned, it's reached the optimal point, because maybe in that case, maybe discriminator hasn't learned to discriminate pretty well between the real and the fake. So that's the like the difficulty of training again, because you train one thing at a time. You train G, and then you move on to training D, and then you move on to training G again, and then you move on to training D. So just by looking at the loss value of one loss value respectively, like you look at the loss value of D or you look at the loss value of G, you can't really guarantee how well it is doing, because your G might be doing well, but in that case your D might not be doing well. And if your D is doing well, then maybe your G might not be doing really well. So there's no like principled way of telling like if you've reached an optimal point. So we'll talk about that later in the lecture. And can it be different depending on the problem? I guess sure. Yeah, you never really know. Like I guess it depends on it depends on your hyperparameters or your random seeds. Like not just on the data set, but like how many layers, how many convolutional layers you use in the G, or how many layers you use in the D, or like the learning rate and all that, like, you know, all the knobs that you can turn in training the neural network, all the hyperparameters, that will affect your training process, and that means that'll lead to different optimal point. So yeah, training again is a pretty tricky process actually. As opposed to training VAEs. Like when you're training VAEs, if your reconstruction loss is like pretty okay, if it's looking okay, then you are pretty sure that you've reached a certain like a preferred point. And in the same manner, if you look at if you're training the autoregressive models, the pixel CNNs and GPTs, you can look at you can calculate the log likelihood, because you're explicitly modeling the PX or log PX. So you know when you're doing a good job. But in GANs, you never really know when you're doing a good job. That's the problem. All right. So moving on. So yeah, we've talked about the minimax game. So in reality, if you use the true min-max term here, if you use the true min term here for training G, it doesn't really work very well. That's because if you think about it, initially, so G is trying to fool D here using this term, trying to minimize this term. But initially, it's so easy for D to discriminate between the real ones and the fake ones, because G hasn't learned anything, right? In the earlier rounds of training, G hasn't learned much, so it doesn't generate a very good, like high quality images or high quality samples. So it's really easy for D to distinguish between the real ones and the fake ones. So that means the gradients won't flow very well, because D, like here, this term will almost always be 0, because this GZ will be a very low quality fake samples. So in that case, D will certainly know to, you know, discriminate or to classify that as 0, the fake ones. So this term will almost always be 0 in the initial rounds. So that means this going to 0 means that this entire thing will be just log 1, which means that's also 0, right? So the entire thing goes to 0, and that means your gradients will look very flat. Because if you look at the log 1 minus D term here, so depending on your DGZ, and if this is your log term, this is your log 1 minus D. This line here is your log. I guess 1 is kind of like it's hidden by the arrow here. It's a log 1 minus DGZ. So if DGZ go to 0, if this whole thing goes to 0, if this whole thing goes to 0 like this, then your gradient of this term will be like quite flat here. If it was around somewhere here, if it was around here, then the gradient will be like this. So then your gradient will have some meaningful value, and then you can use that value to update your parameters of the G. But if DGZ like focuses on the 0 here, then your gradients will be like very flat, and then your parameters won't be updating very well. I mean, the theta G parameter won't be updated very well. So that's the problem of using the original formulation. So in that case, we can actually tweak this a little bit. So instead, we use this term. So instead of minimizing this term, you actually maximize this term. So you no longer have the 1 minus term here. So you remember that log 1 minus D G Z was there before, but we just forget about the ones, and then we just erase this, and then instead of minimizing, you maximize this term. It's the same thing. I mean, semantically, it's the same thing. I mean, mathematically, it's no longer now min-max game, but semantically, it's the same thing. So exactly written here. So instead of minimizing the likelihood of discriminator being correct, you want to maximize the likelihood of discriminator being wrong. So semantically, it's the same thing. You can, and graphically, it's you can see here. So instead of using this log 1 minus dg0, you use log dg0 here. And when your dg0 is 0, so initially, as I said, g0, like discriminator will be, it's easy for a discriminator to receive the fake samples and just discriminate to zeros. So dg0 will be like here in the initial rounds. And in that case, your gradients using the modified term, your gradients will be meaningful now. It won't be flat anymore. So your theta g will be updated better than before, basically. But the problem is it's no longer a minimax game now, because it's a max game. So you're maximizing the terms. It's a max game. So there's no need to discuss all the Nash equilibrium and all that, because now we're not even using the min-max game anymore. But in reality, this really helps. So if you use this term, it doesn't train variable. But if you use this term, like this, kind of like the must term. Like you rarely use the original GAN. You usually use the modified GAN. Right. So moving on. So this is the entire training process. It's a pseudocode. Oh, some questions. So 성준님. So the question is, is the reason for never reaching the true Nash equilibrium, one, is it because of the modified objective, this one, or is two, is it because we're oscillating? It's both. Is it because we're alternatingly updating DNG? So if you use a modified objective, we're no longer even playing the minimax game anymore. So we don't need to talk about Nash equilibrium anymore. But even so, even if you're using the original objective, still there's oscillation. So you can practically not reach Nash equilibrium. So both reasons are valid. But even if we're using the original objective, because we're using stochastic gradient descent to train S and train DNG alternatingly. So it's probably it's really yeah, I don't think you can reach Nash equilibrium. There's probably a rigorous proof somewhere out there that why you cannot, but it's just it's kind of like a consensus. I'm not sure if I've ever seen a rigorous proof, but it's generally, yeah, people say that you can, like when you use SGD, you can't reach Nash equilibrium, which is because of the oscillating characteristics of DNG. Right. So would the objective be the same if we change the generative objective from min prop to max prop such that would the objective be the same if we change the so yep, that's what I did. So I'm looking at the question from G. So yep, that's what I just changed. The change was that we changed from here to here, right? So that's what we did. And the question is the objective the same? So no, the objective function has changed. So it's no longer the same objective, but semantically, the core message is the same. It's just that it's exactly like written as here. Before, for discriminator, the job of the goal of the discriminator was to correctly distinguish between the fake and the real. And originally, the objective of G was to minimize the performance of the discriminator. But now we're maximizing the error of the discriminator. So it's like, I guess, conversely, it's the same. if you think about the 대우명제 and all that, so it's the same semantic. It's just that the mathematically it's modified objective. So it does not have to be min-max game, like, because obviously this works even better than the true min-max game. The max-max game works better than min-max game. It's all about how you can actually implement GAN and generate high quality fake images. So yeah, obviously it doesn't have to be min-max game. As long as it works, it's all good. Nash equilibrium은 이론적으로 min-max game에서만 가능한 것인가요? That's a question that I probably cannot answer, because I'm not a game theory expert. What I learned or read is that when you're playing a zero-sum min-max game, the solution to the min-max game is the same as Nash equilibrium. So that's as far as I know. I guess there are a lot of variety of different types of like games, I guess there could be max game. Like I'm not really sure. Yeah, there's like zero-sum game, there's non-zero-sum game, and I'm not sure like how Mr. Nash, like what kind of theory he came up with, and what kind of like Nash equilibrium there could be, like different versions of Nash equilibrium in different scenarios of games. Not really sure, but yeah, I probably can't answer that question. 마이너스를 붙이면 민으로 만들 수 있는데 그럼 민맥스 게임이 되나요? 맥스맥스 game. Okay, so I guess you answered your own question. Yeah, it doesn't really matter. So yeah, I mean, the theory is all good, but the theory is quite irrelevant when you are training the GANs these days. Like there's a whole different varieties of GAN variants these days. Like there's something called GAN Zoo. You can look it up on the internet. There's like, I don't know, 100 different variants of GANs, and probably none of them actually care about the Nash equilibrium. I mean, maybe some theory papers could, but reality is that you want to tune or modify the GAN so that you can stabilize the training procedure, because that's one of the drawbacks of limitations of GAN architecture. It's really hard to stabilize the training process. So, and when you think about all the practical aspect of GAN, you no longer care about the Nash equilibrium and all that. As long as it trains well, you're satisfied. The question is, modified G objective function 써도 가속 결과 real fake를 디스크리미네이트하고 싶다고 정의를 구하는 것을 만나요. 네, 그렇죠. 만약에 G가 정말로 fake 샘플을, 기가 막힌 fake 샘플을 제너레이션 할 수 있다면은 디스크리미네이터는 50대 50으로밖에 랜덤 게싱밖에 할 수가 없죠. 근데 보통은 그렇진 않습니다. 보통은 디스크리미네이터가 훨씬 더 쉽게 이겨요. 왜냐면은 하이 퀄리티 이미지를 제너레이션 하는 건 진짜 어렵거든요. 근데 그거에 비해서 이게 페이크냐 리얼이냐를 구분하는 건 쉬운, 그거에 비하면 상대적으로 쉽기 때문에 보통은 디스크리미네이터가 제너레이터를 훨씬 더 압살합니다. 네. 그래서 그거를 안 그러도록 하는 게 이게 핵심이에요. 그 트레이닝 할 때. 디스크리미네이터가 너무 잘하면은 이게 제너레이터가 배우기가 좀 쉽지가 않은데, 그걸 이제 어떻게 잘 튜닝을 해주냐가 이제 핵심입니다. All right, so we're gonna look at the pseudocode here. So, because there are two phases, so there's the updating the D phase, updating the G phase. So here, this is the updating the D phase. This is updating the G phase. So when you want to update your parameters of your discriminator, obviously you need to see both samples, the real samples and the fake samples. So here you take M samples, M noise samples, and you take the M actual samples, and obviously you need to put these noise samples through the generator here, and then you want to maximize the cross entropy. So this is a gradient ascent. because you want to maximize this term. So it's a gradient ascent. And you're updating theta d. So you don't do anything with respect to theta g here. You're only updating the theta d in this process. So given some samples, some fake samples, some real samples, you update this term using gradient ascent. And then once you've done that, for k steps, you do it like maybe 1 time, maybe 2 times, or 3 times. It's really up to you. You update your d for some number of times, and then after you've done that, you move on to the updating g part. So you sample mini batch of noises. So in this case, you don't need the actual samples. You only need to sample from the noise and then put the noise through the generator G, and then you're updating the theta G such that this is maximized. So it's again gradient ascent. It's as I said, it's not min-max, it's max-max, right? So you do gradient ascent for both terms. So in this case, you only update this term, this term here, right? So that's the whole process of GAN training. And I hope that just by looking at the pseudocode, you can actually copy this to the PyTorch code. And this setting the appropriate number of k steps is kind of the key. Like, what's the best value for k? Like, how many times do you want to update your discriminator before moving on to updating your generator? And you don't want your generator to dominate the discriminator. You want your discriminator to, like, be able to appropriately tell between the real and the fake, right? So that the G can learn to fool the discriminator. Like your D, like shown here. In order for G to learn to mimic the true data distribution, the D needs to be like, the D discriminator should perform like really well in order to actually use the D boundary to fool. In order to fool D, the D must be a good performer already. So you want to spend some time here so that the D is a good discriminator so that the G can learn to fool it. But so the number of K is really up to you. But people just say like K equals 1 is like sufficient. Like you just need to update K 1 time and then move on to G. Or some people say it must be at least 2. Like you want to update your discriminator at least twice before moving on to G. But I don't think there's like a golden rule here. As long as it's like, if you set certain number for K and it works, then that's the good number. Like it can be 1, it can be 2, it can be 10. Doesn't matter. If it works, it's good number. So like it's very like a lot of the GAN training process is very like intuition driven, and it's very heuristic because there's no golden rule. And of course, there are some GAN variants out there that can help you minimize this kind of like human effort, or this heuristic, like remove this kind of heuristic based approach. So like there's like Wasserstein GAN and WGAN GP. There's BGAN, there's EBGAN. There's like a lot of GAN variants out there. But still, there's some amount of like tuning involved when you're using GAN. All right. Okay, some questions. Is there any specific meaning in K steps, such as MK dataset? No, not really. Yeah, there's no meaning in K step. It's just that you want to set K to some number that works well for you. D가 더 잘하면 G의 for loop으로 학습을 시키는 게 자연스러운 건지 아닌지. 그러니까 왜 G에서는 for loop을 안 하냐, 요 말씀이신 것 같은데, 뭐 사실 이것도 for loop을 써도 됩니다. 이제 여기도 for loop을 쓰고 여기도 for loop을 써가지고 그냥 적절하게 파워 이 업데이트의 숫자를 안대해서 잘 되기만 하면 돼요. 사실 그 정답이 없습니다. 그냥 이거 한 번, 이거 2번 하셔도 되고, 이거 2번, 이거 한 번 하셔도 되고, 이거 2번, 이거 2번 하셔도 되고, 그냥 잘 되면 그게 답이에요. 네. 근데 그거 말고도 튜닝할 그 건수들이 정말 많기 때문에 사실 뭐 러닝 레이트도 해야 되고, 뭐 D에 뭐 레이어 몇 개 쓸 거냐, 뭐 G에 레이어 몇 개 쓸 거냐, 뭐 이런 것들이 굉장히 튜닝할 게 정말 많기 때문에 사실 이게 경험이 되게 중요한 모델입니다. All right, so when to stop training? So as I said, there is no golden rule because D and G oscillates. We never reach Nash equilibrium anyway. And since we're using the max loss, So we don't care about Nash equilibrium anyway. So theoretically, it's all good, like Nash equilibrium and all that. The zero-sum game, the two-person game, the game theory, it's all good. It's very appealing. Doesn't really matter in reality. And the typical ways to generate. So when to know, like how do you know when to stop training? Typically, you generate fake samples from time to time, like every 10 iterations or maybe every 100 iterations. You generate some samples using the generator G, and then visually see how good the fake images are, and then you know that you've reached some good point, and then you stop the training. So, like if there's no visual improvement, like if the generator is already generating good fake samples, then you're satisfied and you stop the training. Or you can use some evaluation metric, like some score, FID score or inception score, that is like a proxy for to score how good quality your images are. So you can use evaluation metric as well from time to time. Or you can use some GAN variance, like faster staying GAN, some GAN, like some GAN variance theoretically guarantee that the longer you train, the better result, the better the outcome. So faster staying GAN or W GAN is one of the examples. In faster staying GAN, like if you train long enough, like if you train longer, the longer the better. All right, moving on. So how do we generate fake samples? It's a pretty simple question. If you've trained your generator, how do we sample fake samples? Pretty easy. You just sample from PZ, which is usually uniform distribution or Gaussian. You sample from PZ and then you put that through a generator's GEZ, and then you get the fake sample, and that's it. Very simple, right? It's super simple. So it's generating fake samples is super easy compared to, I guess in the VA it's the same. Like you sample from PZ, which is normal uniform Gaussian. So N0, 1, and then you take that Z into P X given Z, and then you get X prime. So it's quite similar. The process is quite similar between the VAE and the GAN. It's just that in VAE, this here PZ is, you assume that the samples live in a meaningful latent space, which the latent space happens to be the Gaussian distribution. But here in GZ, you don't really care about what kind of distribution the X's lie in the latent space. You don't care about all that. It's just that you have a very powerful generator that can just map random noise into a real data. So that's it. And there's something called mode collapse that you should be really familiar with when you're dealing with GAN. So because it's an adversarial game between G and D. So what if G generates one very realistic fake sample that can always fool D all the time? Because for G, as long as G can fool D, it doesn't really matter whether it generates diverse examples or just one very realistic sample. It doesn't matter for G, as long as G can fool D. So this often happens. This is called mode collapse. So when G generates samples of limited diversity, often maybe even like one or two samples, like if it just learned to, it kind of like, it's like cheating. The G has learned to cheat the game by generating very limited number of realistic samples, like maybe one person, like maybe one dog or one cat. Like it generates one very realistic image to fool the discriminator all the time. And ideally, if G generates one realistic samples all the time, then D will learn to classify that one realistic sample as 0, the fake. It'll learn to do that theoretically, but maybe D is trapped in a bad local minima. So maybe D cannot do that. So in that case, G is cheating and it's always winning the D. So in that case, your entire GAN is in a mode collapse. So yeah, this often happens when you start training GAN. Like if something goes wrong, maybe the hyperparameter is wrong, maybe the architecture is wrong, maybe something could go wrong, and then when you start generating samples from G, it'll always generate the one realistic sample all the time. So then you know that you have fallen into mode collapse. And the remedy is, of course, obviously you can tune your hyperparameters. You can like restart the whole training process, or you can tune your learning rates and all that, and you can restart training process, or you can use some GAN variants. Again, as I said, like Wasserstein GAN or unrolled GAN. Like there are a lot of GAN variants out there that claims to alleviate this mode collapse problem, right? I mean, I won't go into like, there are like million GANs out there, so I can't go into all the details of what they are. Just remember that there's such a thing called mode collapse, and you will run into it if you're not careful. Yep. So okay. Unfortunately, we don't have a lot of time, so I'll just skim through the rest of the material. So VAE versus autoregressive versus GAN. So here I'm picking pixel CNN, which is the representative example of the autoregressive model. These are all back from the. Oh, actually, this should be GAN. Sorry about that. Yeah. So these are all back from like 2014, 2015. So there were the competitors out there. And these are all different examples from the VAE model, pixel CNN model, GAN model. And if you're using vanilla VAE, so this is like, I mean, there are a lot of VAE variants out there as well to improve the quality of the generated samples. But if you're using just vanilla VAE, vanilla pixel CNN, vanilla GAN, then the GAN shows like the best performance. When I say best, it's like the sharpest image. Like VAE typically generates a very blurred image. It's kind of like the thing that is kind of the artifact coming from using the reconstruction loss. So using the mean squared error kind of leads to generating blurry images like this. It's all blurry. And compared to that, GAN generates very sharp images. I mean, the realisticness, like the quality of like how realistic the images are, yeah, there's like some trade-off. Like example here, it's not as high quality as we would hope it to be, but still the crispiness, like the sharpness of the image is all there. And pixel CNN, I guess it sits somewhere between VAE and GAN. Like it generates pretty good quality images. It's just that they're usually slow in the inference. When you're generating images, it takes some time. Right, so VAE is, you generate sample from Gaussian and then use the decoder. And measuring the performance is pretty simple. You have a real image, and then you put it through the encoder and decoder, and then you get the reconstructed image, and then you can calculate the reconstruction loss between the X and X prime. So that's how you measure the performance of VAE, as long as like generating samples go. And image quality, as I said, it's kind of blurry, as this is due to mean squared error loss. And of course, modern VAs generate better images. Like these are just vanilla VAs. So these days, there are like a lot of VAE variants out there. Compared to pixel CNN or autoregressive models, generating it's kind of a iterative process. So given some initial pixel, like if there's like some n by n image, you give like one or maybe some number of pixel, maybe one pixel randomly chosen from some distribution, and then you start from here. You generate like this. You like this. You take the for loop and then generate one pixel at a time. And so because of that, it's a relatively slow generation process. But measuring performance is very straightforward, because you are actually estimating, or you're modeling you're explicitly modeling the data distribution, the image distribution, by factorizing it. So you can actually calculate this value for your X prime. You sample a new fake image, and then you can actually derive this. You can calculate this value by simply multiplying all these. And of course, you want to calculate the log probability rather than actual probability. So you can actually calculate the log likelihood of your sample, and that's how you know the performance of your model. And the image quality is probably better than vanilla VAE, and modified autoregressive models exist out there to speed up the generation process. I mean, yeah, like the autoregressive models was kind of a hit back in the days, and people used to work on this a lot. But these days, I think as long as generating high quality images goes, people just converge on using GANs these days. For GAN, generating is pretty simple. You sample from some random noise, and then you use the generator. Measuring performance is still, I haven't talked about this yet, but measuring performance is still is an issue. Image quality is the sharpest quality. So style GANs is a modern GAN that can generate a very high resolution images, like 1024 by 1024. It's a very high quality images. It even looks like a realistic person. You can go search internet and search for style GAN, and you can look at the fake samples, and you can, I don't think you can distinguish between the real ones and the fake ones. But the problem is the mode collapse still lurks. Right, evaluation. So it's already 12 o'clock, so I'm gonna just skim this because I don't think there's you won't be implementing FID score by yourself. You'll probably just use some algorithm out there, but it's probably good idea to grasp the concept of what they do, like inception score or FID score. Probably you've heard about this a lot when you're using GAN. So because GAN uses an implicit distribution, you don't care about the latent distribution. It's just random noise, and as long as you sample good quality images, you're happy. So unlike VAE or Pixel CNN, you don't know the distribution. So that's why it's difficult to measure the quality of fake samples, because you don't know where it's coming from, right? So you can't calculate the likelihood, you can't calculate the reconstruction image, reconstruction values, reconstruction loss. There's not much you can do. So that is why you use some other metrics called inception score or Frechet inception distance score, often called FID score. Right. So before we do that, I hope, I guess, for those of you who have other schedules, I just want to skip this and then move on to the application side of the GAN, the recent ones. So, and then after that, I'll talk about the FID and inception score and FID scores briefly for those of you who stick around. So I'm going to talk about this first. So I picked 3 quite, famous, popular applications. I mean, I don't know all the GANs out there. There are like a million GANs out there. So, but I just chose 3 that I personally like. So one is from researchers from DeepMind. So it's text to image. Not exactly DeepMind. As Scott Reed was a PhD student at the time he was working on this, I guess. So anyway, so it's called text to image GAN. So you generate fake samples given a text as a condition. So it's a conditional image generation. So there are some samples here. So given some text like this small bird has a pink breast and crown and black primaries and secondaries. And then given this Q text, the GAN is able to generate these diverse images. They are all, well, first of all, they are all birds, and they have rather pink or pinkish red breast, like here, like red, I guess you could call this pink or red. And then they have like certain, crown. I'm not sure what crown or primaries and secondaries are. Anyway, they look like a bird at least. And if you look at this, like white and yellow flower have thin petals and a round yellow stamen. Yeah, I don't know what that is either. But at least you can see that there's like white petals here, as suggested by here, white petals. And they are all slightly different images. Like they're not exactly the same. I mean, they're pretty similar, but at least the details are different. So you can see that you can use GAN architectures to generate conditionally based on text encoding. So this is one of them. Another thing is even this very famous, very popular model called CycleGAN, and it's it enables you to transfer style between 2 domains. So you can change, but this is like the representative example, like changing zebras to horses. So if you have an image of a zebra, then, and if you have if you have a set of images from zebras, and if you have a set of images for like just horses, like brown horses, you can use those 2 to adversarially train your GAN to transfer style between the 2. Like you can transfer, you can transform the zebras into like ordinary horses, or vice versa as well. You can transform brown horses to zebras. You can totally do that. Or maybe even summer images to winter images, or photographs to like various art style, like Monet style, Van Gogh style, Cézanne, or ukiyo-e style. Yeah. So it was like a very interesting concept. So yeah, if this still is a really popular model. Like you can, if you go to the internet, there's like a lot of applications where you can take a picture of yourself, and then and some app will turn your picture into like a Disney style character. Like if you're a woman, it'll turn you into like Disney princess or something. So that is all based on like CycleGAN actually. And even more recently, so this is something called StyleGAN that I talked about, that can generate high resolution images. It uses a lot of techniques. I won't go into detail, but this is this is a sample that I just scrapped from the internet. So this is a 1024 by 1024, and you can just look at the quality of the image, like the strand of hair all here, the wrinkles like here. I mean, it's just as good as a real person. The texture of the hat and all that is just phenomenal. So, I mean, you can really kind of imagine some person looking like this living somewhere in the world. This is totally fake, by the way. This is totally fake. This is not a image of a real person, but could be, you know, it's so good. It's so high quality. It could be a image of a real person, right? Okay, so yeah, these are the 3 representative examples. But as I said, there are like million GANs out there. So if you're interested, you can look up the GAN Zoo or some GAN applications on the internet. Then, as you know, pick some model of your liking, and then work on that. All right, for those of you who still have a bit of a time, I can go through the evaluation thing, the inception score and FID score. And if not, you can leave whenever you want. All right, so what inception score is, given an image without any like known distribution or like GANs don't have real image. It's you just sample from noise and then turn that into a image. So there's no reconstruction loss as well. So in that case, you can use something called inception score. And the reason that is called inception score is because it's using a model named inception model. It's specifically a version 3. So inception model was developed by people from Google, and there are a lot of versions. There's inception version 1, version 2, version 3. I think even there was version 4 or something. And inception version 3. So inception models are trained on ImageNet, which means that there are 1,000 classes. So ImageNet. So the inception model is trained for classifying images into 1,000 different classes. And you're using this model, pre-trained model, to evaluate your quality of your fake images. So it must be pre-trained already. It must be pre-trained on ImageNet. So it's a Inception v3 pre-trained on ImageNet, and then you're using that to evaluate the quality of your fake samples. And the architecture looks like this. I mean, it's a pretty gigantic model. And yeah, I won't go into detail, but it's like a chain of convolutional neural networks and pooling and all that. So the reason for using inception score is there are 2 criteria. So first of all, you want to evaluate the quality of your image, like how good is how realistically looking is your fake image. So that is your image quality. So if your image looks like if your fake image looks like a real stuff, like a real object, then I mean, so I'm sorry. So if the higher the quality of your image, or the more realistic the realistic your fake image is, then it must look like some object, like a bird or a car or a bicycle. It must look like some object or some class, because we are using Inception v3 model which has 1,000 classes. So it must your fake image must look like some class. Another criterion is diversity. So you don't want your generator to generate like all birds all the time or cars all the time. You want your generator to generate like birds or cars or people, bicycle, buses, like shoes, whatever, some diverse set of images. So it must be a wide range of objects generated. So in that case, in that sense, image quality can be measured by a by a conditional probability using the inception model. So you have an inception model, inception model, and you have a fake image X prime, and then it must be classified into one of the 1,000 classes, right? Like bird, a car, a person, something like. There are like 1,000 different classes. And if your fake sample is a realistic object, then it must be classified into one of the many classes. And hopefully, like out of 1,000 classes, only one class will have a very high probability. Like if it looks like a real bird, then the probability must focus on the bird, and it'll be 0 to all the other classes. Like it must be 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? Because if it looks like a bird, then it must be the probability score should focus on the bird only, right? So that means if there's a focus on a single class, then your conditional probability must have a low entropy. So that's the principle behind the inception score. Like your conditional probability should have a low entropy. That means like assuming that guarantees a high quality image. And as far as image diversity goes, your marginal probability py over all images should not focus on one class. So if your generator generates bird images all the time, then your entire py given x will always be 1, 0, 0, 1, 0, 0, 1, 0, 0 all the time. And this is not what you want. You want 1, 0, 0 sometimes. And sorry about that. You want 1, 0, 0. Sometimes you want 0, 1, 0, 0, 0, 0, 1, or 0, 0, 0, 0, 0, 1. Like you want a diverse sample, diverse conditional probability, because you want your generator to generate diverse images, right? So your py over all images should not focus on one class. That means py should have a high entropy. So if you take all these and calculate the entropy, then it should be a high entropy. So that guarantees diverse images. So it's a game between. It's not exactly. It's a yeah. You take it's a correct. You have two aspects that you want to consider when evaluating your set of fake images. So in that case, you want to calculate the relative entropy of pyx and py to be large. So you want pyx, a single conditional probability, to be low entropy, and your marginal probability to have high entropy. So it's a relative entropy. You want the relative entropy to be large. And it happens to be that the KL divergence is actually a relative entropy. So if you look at Wikipedia, the definition of KL divergence, Kullback-Leibler divergence, sometimes you call that relative entropy as well. I mean, if you look at the equation, the KL divergence is actually log P minus log QP, negative out there. So it, like if you take this side, this is an entropy of P, and this is like another, I guess, conditional entropy or some other types of entropy. So it's a relative entropy, basically. So when you want to maximize, you want the relative entropy of py given x and py, or KL divergence between the two, to be large. So the larger the score, the better. Specific algorithm, I put it in the appendix after the last slide. Basically, so I mean, you don't use the KL divergence directly. You do some manipulation to the KL divergence so that your worst score of inception score is 1.0. So the worst score you can get is 1.0. So if you and the best score you can get is n, such where the number n is the number of output classes of a pre-trained model. So if you're using inception version 3 as your like reference model for evaluating your score, then it has 1,000 classes. So the best score is 1,000, right? So that's your best score. Worst score 1, best score 1,000. So if you, for example, this is just an example. If you have a distribution like this, conditional probability like py given x1, py given x2, py given x3, And it's 100010001. This is like the ideal case. Individually, it has a low entropy, but marginally, the overall distribution has a high entropy. So in that case, the best score could be achieved, which is 3, because there's like three-dimensional output classes. So it's 3. On the other end, the worst score that you can get is when you have distributions like this. So individually, it's high entropy. Like it could be either this class, this class, this class. It's the same. They have the same probability assigned to all different classes. And overall, marginally, they're the same probability. So in that case, you have the worst score, which is 1. So in that case, the inception score will be 1. So this is the intuitive, the principle or motivation behind the inception score. People still use this quite often, but these days FID score is probably a bit more often used than inception score. So FID score is you still use inception. That means it's inception, the Frechet inception distance. So you still use the inception version 3 model. It's just that you don't use the output probability py given x, something like that. Instead, you use the last pooling layer, sometimes called like the hidden features or image features, or feature vectors of image. So that means right here. So suppose that this is gives you a 1,000 dimensional output because your inception model is generating 1,000 output classes. So right before that, this is the penultimate layer here. You take this layer, this hidden representation, as a image feature, and this happens to be 2048 dimensional vector. I mean, that was how inception version 3 model is configured. It uses 2048 dimensional vector in the layer right beneath the output layer. And the intuition or the motivation is that you want to compare the distributions of the features being 2048 dimensional vector, features between real and fake. So you put a lot of real samples here and a lot of fake samples here, and then you will derive a lot of 2048 dimensional vectors from both groups. And then you want to calculate some distribution, like mean and the standard deviation and all that. And then you want to use those statistics to compare the distribution between this and this. So the idea behind it is that you want to view the image feature, 2048 dimensional vector, as some kind of like multivariate Gaussian distribution. Then you calculate distance between the real Gaussian distribution and the fake Gaussian distribution. And when I say distance, you use something called Frechet, and it should be out there. You use something called Frechet distance to calculate the distance between 2 Gaussian distributions. And Frechet distance is sometimes called Wasserstein 2 distance. These are like all like, mathematical stuff that I won't go into detail. I mean, I don't really know the details of why it's called Wasserstein 2 distance and all that. It's just that suffice to say that it's a distance between 2 distributions. So it's a distance, so it's not a divergence. So it's distance, so it's like all the like commutative and all that property holds. And because it's a distance, the larger the value of FID, probably worse the result, because you want the fake distribution to be as similar as possible to the real distribution. That guarantees high quality fake images, right? So the higher the distance, the worse the quality. So ideally, you want your FID score to be 0, which is like there's no distance between the two, right? Yeah. So it's so first of all, in order to calculate FID score, you need to calculate the feature-wise statistics. Feature-wise being the feature was 2048 dimensional vector of fake images and real images, right? And then you calculate the mean and the covariance matrix for the real and fake features. And then given the mean and covariance matrix, this is how you calculate the Frechet distance. So this is your Frechet distance definition, like this. So you take the mean from the real, mean from the fake, and then you calculate the square distance between the two. And then you take the trace of a covariance matrix, some manipulation of covariance matrices. So covariance matrix, and then this is like the square root matrix of your product of your covariance matrix. And I mean, you don't need to know all that. You can just simply call the functions from NumPy or PyTorch if you want to implement this. Probably you don't need to implement it. Like there's probably already an implementation out there that will give you a FID score. Like if you just put the 2000, if you put like 2048 dimensional vectors in one spot, like real ones and the fake ones to the function, then it'll just calculate the FID score for you. But if you want to if you want to implement yourself, then yeah, just follow this expression. Right. All right. So yeah, as I said, the lower the FID score, the better the sample quality, the better the fake quality images, and better the fake images quality will be. So in the paper where the authors introduce the FID score for the first time, they actually have some interesting examples. So they manipulate the images in different aspects. Like they put some noise here, or they blur it, or they distort it. Like I guess it's kind of like a rotational distortion, or they put another type of noise into it. And the more you put more noise into the image, the FID score goes higher. So the best FID score is of course 0. So it was kind of like the 0 here. And the more noise that you inject into the real sample, the FID score becomes like 200 something, 220 or something. And the same goes for all other like disturbance here. So there's disturbance level. So different types of disturbance. If you blur it, FID score is sensitive to blurring as well. If you distort it, FID score is sensitive to distortion as well. Another noise injection FID score also responds to that. So the message here is that FID score is a robust measure that is sensitive to a lot of different types of disturbance. Like not sure if people did the same thing with inception score, but as long as like this is like a good example or a good motivation why FID score can be good evaluation metric for your fake images. So people use this a lot, and there are whole different other metrics out there like PSNR, or LPIPs or SIM score. Yeah, there's a lot of different measures out there, and people use a lot of people use ensemble of measures, like plus FID, maybe even like IS, inception score. Like they use ensemble of different measures to evaluate the quality of their images, to convince people that their fake images are realistic as it gets. Right. Some questions out there. So inception score는 ground truth가 없어도 계산 가능한 FID score GT images. 네, 바로 그겁니다. So that's a very good point. So 안성경 pointed out that inception score doesn't require real images, but FID score does. So that's why FID score is a better measure. I mean, that's why the authors claim that the FID score is a better measure than inception score, because inception score, you just take the fake images and put it through the inception network, and then just based on the outcome, the PY given X and PY, you just calculate the score. So if you happen to use, if you want to generate like I don't know, if you want to generate realistic photo like images, like ImageNet images, then inception score is probably a good idea. But if you want to generate some cartoonistic images, then when you're using inception model to evaluate your cartoon-like images, it's probably not a good idea, because inception models are already trained on ImageNets, which are realistic images. So in that case, inception score is probably not a good idea. So if you want to generate cartoon-like images, then you want to use both real cartoon images and fake cartoon images, and then use FID score to compare the distribution between the two. 그리고 경희연 Park is 샘플한 true fake image들로 Gaussian distribution 추정해서 스코어. 네, 맞습니다. 네, 맞습니다. 그래서 true 이미지들은 이미 있고, 어차피 겐을 학습할 때 이제 true 이미지가 있어야 되니까. 그 다음에 이제 겐 학습한 다음 나온 페이크 이미지들을 이제 뭐 대충 몇만 개 정도, 보통 한 몇만 개 정도를 씁니다. 이제 이 FID 스코어를 계산할 때는 몇만 개 정도를 써가지고, 뭐 true 5만 개, 뭐 fake 5만 개 정도 써서 이제 샘플한 다음에 그걸 이제 각각 5만 개를 전부 다 2048 디멘셔널 벡터로 바꿔놓고, 인셉션 스코어 이용해서. 그다음 그거를 2048 디멘셔널 가우시안 디스트리뷰션이라고 가정을 한 다음에 둘 사이의 페이크랑 리얼 사이의 프레쳇 디스턴스를 계산을 하는 겁니다. 그래서 디스턴스가 크면은 안 좋은 거고, 디스턴스가 낮으면 좋은 거고, 그런 겁니다. 인셉션 모델은 1000개 카테고리를 학습된 건데 얼굴 이미지만 가지고 FID를 구해도 잘 나오는 건가요? 근데 일단 인셉션 모델은 추가로 학습시키지 않고 사용만 하는 거 맞습니다. 그냥 이미 학습된 거 픽스 시켜놓고 그거 그냥 이밸류에이션 하는 데만 사용하는 거예요. 그리고 이제 인셉션 모델은 인셉션 모델 1000개 얼굴 이미지만 가지고 그러니까 이미지 1000개 카테고리 학습된 거는 맞는데 이제 그거를 그냥 대리로 사용을 하는 거예요. 그러니까 1000개의 카테고리를 학습을 했기 때문에 이제 다양한 리얼 이미지들을 봤을 거라는 가정하에 인셉션 모델이 이미 이제 다양한 모델의 이미지, 다양한 디스트리뷰션 이미지를 봤을 거기 때문에 그 중에서는 얼굴 이미지도 있을 거고, 그렇기 때문에 이제 얼굴 이미지만을 내가 생성하는 겐을 만들었어도 FID 스코어를 이용한 학습 스코어를 매기는 데 있어서는 인셉션 모델을 써도 크게 무리는 없다 정도로 보시면 될 것 같아요. 네, 그리고 명지윤님, 2048기간의 민을 구한 건가요? 샘플 10,000개의 민. 그러니까 2048개의 이 히든 디멘션이 있으면은 이게 하나만 있는 게 아니라 이제 그 페이크 샘플이 여러 개 있을 거 아니에요. 이제 페이크 샘플 X 프라임 1, X 프라임 2, X 프라임 3에서 쭉 있을 텐데 페이크 샘플 그 2048 디멘션들이 각 디멘션마다의 민을 구하는 거예요. 그러니까 얘의 민 전체 다 해서 또 여기의 여기의 민 이렇게 디멘션마다의 민을 구하는 겁니다. 페이크 샘플 전체에 대해서. 그리고 똑같은 짓을 리얼에서 또 하고 그렇게 해가지고 이제 그 두 개에 대한 디스트리뷰션, 그 두 개에 대한 디스턴스를 구하는 거예요. 이성준님, 5,000개 리얼, 5,000개 페이크에 대해 각각의 페이크에 대응하는 리얼을 그런 거 아닙니다. 그런 거 아니에요. 각각의 페이크에 대한 리얼 아니고요. 그냥 페이크가 5,000개 있고 리얼이 5,000개 있으면은 페이크 5,000개에 대해서 이 2048 디멘션짜리 그 피처 벡터가 5,000개가 나올 텐데 그 5,000개에 대해서 그러니까 민하고 코비넌스 매트릭스를 구하고 그 다음에 또 5,000개의 리얼 2048 디멘션짜리 벡터에 대해서 또 민하고 코비넌스 매트릭스 구해서 그래서 이제 이걸 계산을 한 겁니다, 그냥. 인셉션 스코어에서 예를 들어 반고풍의 이미지를 만들고 싶을 때 이미지 다이버시티가 모든 클래스들의 균일하게 나오는 게 아니라 원하는 클래스 쪽에서 더 높게 나와야 하는 것 아닌지 궁금합니다. 모든 클래스는 균일한 게 아니라 원하는 클래스 쪽. 그거는 스타일 트랜스퍼에 대한 얘기라서 여기에 잘 맞는 건지 잘 모르겠어요. 네, 슬라이드 좀 남은 거는 이건 아까 보여드린 겁니다. 이 텍스트 이미지 겐, 이거 스타일 겐, 요거 아까 보여드렸죠. 그거 끝난 거고 그 뒤에 이제 이 알고리즘인데 이건 나중에 살펴보죠. 이건 인셉션 스코어 알고리즘이랑 FID 스코어 알고리즘입니다. 수업은 끝났습니다. 네. 그리고 반고풍의 이미지 만드는 거 스타일 트랜스퍼에서 이거는 인셉션 모델이 이게 반고풍의 이미지다라는 거를 클래시파이하는 기능이 없기 때문에 그거에 이 적절한지 잘 모르겠어요. 인셉션 스코어, 그러니까 스타일 트랜스퍼가 잘 됐는지를 인셉션 스코어를 이용해서 매저하는 게 올바른 매저인지 잘 모르겠습니다. 마지막으로 이제 김현경님, 이미 학습된 모델인 스코어 계산 과정 사용자 정의에 대한 모델 정보. 이미 학습된 모델인 인셉션 V3를 이용해서 스코어를 계산하는 과정에서 사용자 정의된 모델의 정보는 어느 단계에서 활용됩니다. 근데 무슨 의미인지 잘 모르겠는데 사용자 정의된 모델의 정보. 그게 무슨 의미인가요, 현경님? 혹시 음성으로 질문해 주실 수 있나요? 네, 뭐 이미 나가신 것 같기도 한데, 네, 저 잘 모르겠는데 혹시 정의된 모델의 정보는 언당에 활용되는 거. 네, 어쨌든가 아까 말씀드렸듯이 이 학습된 모델은 건드리지 않습니다. 인셉션 V3는 이미 학습이 돼 있고 이미지넷에 대해서 그거는 이 스코어를 계산하는 데만 쓰는 거지 그걸 뭐 튜닝하거나 그럴 일은 없습니다. 그냥 갖다 쓰는 거예요. 네. 혹시 뭐 더 궁금하신 거 있으면 클래스 서머로 나중에 물어봐 주시면 답을 해드리겠습니다. 예, 그럼 오늘 수업은 여기까지. 아니 차이는 없습니다. 그냥 똑같은 거예요. DKL이나 KL이나 같은 거예요. 그냥 KL 다이버전스입니다. 네, 제가 다음 미팅 있어가지고 이제 가봐야 될 것 같아서 그 궁금하신 거 있으면 클래스홈에 올려주세요. So if you have any further questions, please post them on Classroom. Either myself or TAs will respond to that. Thank you for listening, and I'll see you guys this Thursday. Bye bye.